Hi guys, today we're going to look at a problem set, and this basically is one of the applications of the concept of derivatives, and also we're going to see that it's going to be basically one of the set of rules that we refer to as Rolle's theorem. Now, Rolle's theorem was formulated by Joseph Louis Lagrange, and therefore we are going to see that this specific theorem is going to place some conditions on functions that we're going to basically see in terms of a graphical set. So this case, I'm going to use an illustration on the board of a graph that is going to be illustrated as such. So I'm going to have a graph being given as such in this specific case, and this is going to be a stretch of the x-axis given as such. So at specific points over this specific axis, I'm going to give points for A and B, which are going to be represented as such. So I can be able to give a set of coordinates for this specific points for the graph of f of x given as such. So this is going to be y is equivalent to f of x given as such, and then therefore I can be able to give another set of values for this range of this is b0 given at this specific point. So in between the function of f of x, we can be able to allocate various points for different gradients, whereby we said that we can be able to find the gradient at a specific point of a function by drawing a tangent that is going to be a tangent. Perhaps at this specific point, I can be able to find the gradient of that specific point using that specific tangent. And in some areas, we're going to see that we can be able to find a tangent which is basically going to, geometrically going to be perceived as a derivative at these specific points. So if I have this point, in these specific cases, these 3 points given as, perhaps I can give this one as point C, D, and just move this one up. So this is a graph of y f of x, and perhaps point E given are those specific points. These are going to represent the range of values for C, D, and E within that A set of course, A and B intervals respectively. So in this specific regard, then therefore we're going to consider a case of a function f of x that is continuous on the interval of A and B, whereby we're going to give this interval as a value of A, which is equivalent to x or greater than x, or meaning x greater than A, and also which is a range of value that is within B but smaller than B given as such. So that's going to be the interval of this specific function of f of x. And we're going to denote the concept of a derivative of f of x, which is a derivative of f of x given as f prime of x given as such. So at any one point, as I said, we can be able to give that specific aspect of a tangent and find the derivative of this function of f of x at those various points given as such. So we can describe various aspects of the interior part of this specific range of points. And now suppose I'm going to find a specific derivative of this point at C, D, and E. This range of values are not going to give me the change, or rather the change in the y-axis, which is of course a vertical change. We said that we can be able to find a derivative of a function, which is of course this is a function f of x, by finding the change in y and the change in x given as such. So this is going to form a ratio of the change in y over change in x. But for these various tangents that I've drawn, which are these specific points C, D, and E, they're going to give me no change in the y-axis. So it's going to be the change in y, which is 0 over the change in x. Therefore, their derivatives are going to be equivalent to 0. So at these individual points for C, D, and E, we're going to have the function of these specific graphs for C equivalent to a function of the graph for D, and the function of the graph for E given as such, and that derivatives are going to be equivalent to f prime over C D and E, which is going to be equivalent to 0, of course. So therefore, we can have values for this specific range of functions, but their derivatives at these specific points are going to be equivalent to 0, as I've mentioned. Then the argument x will have at least one value at this specific point, whereby within this range of values, the derivative of those functions are going to be regarded as or the first derivative of those range of values are going to be given as 0. So we can be able to give this specific value. It can be 1. So suppose I had perhaps a function that is going to be represented using this graph, then we're going to have a single point having that derivative as 0. So we can arbitrarily give this particular value for ct and f as epsilon. So therefore, we're going to give a general illustration for this specific point of a value for ct and e at any one point over this specific range of values for a and b being given as a derivative of epsilon, which is going to be equivalent. So this is our notation, equivalent to 0 given as such. So this basically range of explanation that I've given are going to entail what we refer to as Rolle's theorem. And of course, we're going to see that Rolle's theorem states that the f prime of these specific points for epsilon is going to be equivalent to 0 at least for one point, whereby the f of x is equivalent to this value of epsilon for an interval between a and b. And of course, it's going to be given in terms of an expression. And basically, I'm going to give it as I've done this specific point. So therefore, our question that asks us to show that the function f of x, x minus x cubed on interval, this one and this one satisfies Rolle's theorem. So this is a range of values on the x-axis that are going to stretch between -1 and +1 given as such. And therefore, we're going just to give a general illustration for this specific case for Rolle's theorem and try to apply it and see whether we can be able to find the values of this specific value that we have referred to as c. So Rolle's theorem states that if a function is continuous on the interval a and b and has a derivative f prime of x, as I have explained, at every interior point of the interval, and furthermore that the f a, f b, and f of c, as shown, is equivalent to 0, then the x will have at least one value that is going to be given as epsilon aside, or rather we can just give it as epsilon, which is going to be equivalent to a value in between these values of the range of values of a and b, which of course are the points given for c, d, and e respectively. And this such that of course the derivative, the first derivative for this particular points that are ranging between a and b are going to be equivalent to 0, as I had said. So in going to our example, then therefore we're going to see that we can be able to find the values of this specific function by trying to do a direct substitution for individual values that are going to be found in between this specific range of values that we have given for this one and this one. So therefore, if we try to give it as f of a, so suppose a is -1 for this. So these are going to, if this value for x is going to range between -1 to the left and +1 to the right. So it's going to consist of numbers -1, 0, and 1 as the values of x, as I've said. So for -1, we're going to do a substitution and see that f x for -1 and then minus -1, the cube of -1. So this is going to give us the values of this specific function being given us. So I'm just going to do a substitution, direct substitution for this. So for this particular function, the the function of fx can be represented as f with a substitution of the first value for x, which is a -1. So this is going to be -1 minus -1, which is equivalent to 0. So if I do a substitution for this, then I'm going to find the f of x at this specific point equivalent to 0. And this 0 is going to fall between a range of numbers of the intervals that have been given. So suppose I use 0, so I'm going to have f of 0 over 0 minus 0 to power 3. So this is going to be equivalent to 0 still, as I've said. And then for the f equivalent to 1, this is going to be equivalent to, of course, 1 minus 1, which is also going to be equivalent to 0. So I'd said that for us to obey the first condition of Rolle's theorem, we're going to have this function of f of a equivalent to f of b equivalent to f of c, which is equivalent to 0. So it has satisfied that first condition that we had mentioned for Rolle's theorem, whereby the f of a, f of b, and f of c are going to be equivalent to 0. So for us to find the value of c, or rather to find the value of c, we're going to assume that c is equivalent to this specific value, whereby we have said that this value is going to range between a and b, which is an internal part of this range of numbers for this specific range of values. Therefore, we're going to have this one illustrated as such, whereby we are going to have to do a direct substitution for this, and we come up with an equation whereby this is going to be represented as a minus the cube of that. And therefore, we have stated that for us to see whether it obeys Rolle's theorem, we're going to find the first derivative of this specific function, whereby we're going to have this one being given as this is 1 minus 3, and then this is going to be given as a square of that. So this, we said that for it to obey Rolle's theorem, then we're going to have this first derivative equivalent to 0. And if we try to equate to 0, then therefore we can be able to find the values of this specific symbol, which is equivalent to 1. And therefore, this is going to give us the value of the square of this one equivalent to, of course, a third. Now, if we try to find the root of this one, then we can we're going to find two values for, of course, this symbol, which is going to be equivalent to positive and negative a third. So positive and negative a third are going to fall within the range of these values that I've mentioned. So basically, which is negative 1, 0, and 1. And of course, we're going to see that this basically is going to satisfy the second condition for Rolle's theorem, as this range of numbers for positive 1 and positive a third is going to be within the confines of 0 and negative. So we have shown that this specific equation satisfies Rolle's theorem within this interval. And number 2, that it satisfies Rolle's theorem, and we have found the value of this constant c basically by finding it to be a value of a third, positive a third, and negative a third given as such. So this is how we are going to do an approach for various application areas that we come across, especially in the different concepts in mathematics, physics, chemistry, and biology, as I had mentioned earlier. So that is it for now, guys. Bye, God bless.